Alright, so there's a link to component specifications on Canvas. And once you're on that website, you can look around or wherever. So if you want to get to the syllabi for this course, you can come down to 250 and so on. Alright, let's talk about Demorgan's theorem. So we know Demorgan's theorem says something like this. We can switch between ors and ands by changing how we do the negation. So if we take A or B and we complement that, that's the same thing as anding their complements. And if we take A and B and complement that, that's the same thing as oring their complements. And an interesting property of this is the following. If we take A and we OR it with itself and take the complement, that's the same thing as taking A bar and ANDing it with A bar. And A bar ANDed with A bar, well, X ANDed with X is the same as X, right? If X is true, that's true and true is true. If X is false, it's false and false, which is false. So this is the same thing as A bar, which means we can make an inverter out of a NOR gate. So here's a NOR gate. And if we tie the two inputs together and feed A into that, what comes out the other side is the inverse of A. And if we make a truth table for a NOR, so an OR is 1 whenever one of these is 1. So a NOR is going to be 1 in this case, and then 0 down here. And if we're wiring both inputs to be the same, then there's only two possibilities. Either both inputs are 0, in which case the output is 1, or both inputs are 1, in which case the output is 0. There's your inverter. So we can make an inverter out of a NOR gate. Well, if we have a NOR gate and we have an inverter, what do we get if we put those together? There's a NOR gate. And if we take this and we invert the output, what is this equal to? Think about it logically. What is the output here of this NOR gate? It's not the OR, right? It's the OR with a negation on top. If we take that and we negate it again, logically, what is this output equal to? It's just the OR. This is A or B. And we can make an inverter out of a NOR gate like this. So here's something crazy we could do. We could take A and B, we could put that into a NOR gate. We could take the output, feed it to both inputs of another NOR gate. And we've just made an OR gate out of a NOR. So with a NOR gate, we get a NOR, we get a NOT, and we can also get an OR. Can we get an AND out of NORs? Is that possible? What's your gut feeling? gut feeling, raise your hand if you think we can get an AND out of NORs. Good gut. We've got this thing called Demorgan's theorem, which connects ANDs and ORs together. They're not a straight connection. We have to do some negations, but we know we can do negations with this. So let's look at this version of Demorgan's theorem. A NANDed with B is A bar ORed with B bar. Well, if we have A, we know we can get A bar because we got an inverter. If we've got B, we know we can get B bar because we've got an inverter. And if we have A bar and B bar, we can OR them because we made an OR gate out of NORs. So with a bunch of NOR gates, we can calculate this, which means we can calculate A bar NANDed with A NANDed with B. And if we can calculate the NAND, we can take that and run it through another inverter, and that'll give us the AND. So we can also get a NAND, and we can negate that and get an AND. And once we have ANDs and ORs and NOTs, we can get an XOR and an XNOR, and we can get any logic function that we want. And all we need is a NOR gate. So a NOR gate is sometimes said to be universal. If you have a parts box and all it has is NOR gates, you can build up any circuit that you want. It's a pain, but you can do it. And it turns out NANDs are also universal. If all you have is a box of NANDs, you could build any circuit out of that. Because that's just the other side of Demorgan's theorem. We can do exactly the same thing, make an inverter, make an AND, and then use Demorgan's to get a NOR and then get an OR. So technically, you only need one type of chip, just a NOR gate. Now in practice, we have much more than that. In practice, we have all of these and a whole lot more. So in the 70s, a company called Texas Instruments started manufacturing integrated circuits, and they had a book. It was an orange book, and it was about this thick, and it was just page after page of these kinds of data sheets for all the different chips they made. And it was a 3-input AND gate, and a 3-input NAND gate, and an 8-input NOR gate, and all these different types of chips, and they all had different numbers. They all started with a 74. That's from Texas Instruments line way back when, and it was 74, some prefix, and then a number that identified the type of chip. And so if you needed a 4-input AND gate, you'd get a 74LS21. But, you know, in reality, if you need a 4-input AND gate, we can do some more algebra. Let's say A, B, C, D. So that's the AND of 4 things. Well, remember, this is an associative operation, so this is actually equal to A ANDed with the results of a 3-input AND operation. And B ANDed with CD, B ANDed with C ANDed with D is the same thing as B ANDed with C and D. So Boolean logic tells us that to calculate the AND of these 4 things, first we can AND C and D, and then AND that with B, and then AND that with A. So here's what we can do. We can take C and D, put them into an AND gate, take that, AND it with B, take that, AND it with A, and that's our 4-input AND operation. So we technically don't need all those hundreds of different types of components, but they're a whole lot more convenient than having to build this every time we want a 4-input AND gate. But go back another decade or two before that, and this is the 60s, and what was the big thing technology-wise going on in the 60s? Anybody know? John Kennedy kind of kicked this off. Space race. Space shuttle came later, but the quest to get into space, in particular the quest to get to the moon. Right? So Kennedy launched this in the beginning of the 60s and said we're going to send someone to the moon, we're going to bring them back. No idea how we were going to do that, but a few rocket scientists, literal rocket scientists, convinced him that this was doable and was a good thing to do. So the country started on this mad dash to try to figure out how to build something that would take humans away from gravitational pull of the Earth into space, get us to the moon, get somebody on the surface, bring them back, all this kind of stuff. A lot of computational tasks involved. Computers weren't really a thing back then, okay? Computers were giant behemoths that filled, you know, something twice the size of this room and weighed tons and were very fragile, and how are you going to use that on a spacecraft when, you know, carrying an extra pen is going to cost you X amount of dollars. So this was a formidable task, and a big part of the task was coming up with computer circuits, right? Because you couldn't just go and buy a laptop or a Raspberry Pi or something. And in fact, you couldn't even get integrated circuits yet. They weren't quite a thing. They were discovered in the 50s, late 50s. But Texas Instruments didn't have their catalog of parts, or you couldn't go into the collaboratorium and open up a Tupperware container and grab some parts, right? That would have been like a world changer if you could go back and do that. But there were no such things. So the government contracted with MIT to solve this problem. And the question was, how are we going to build these computers in a reasonable way? Well, the first thing they had to do was come up with chips. And designing a chip to put onto a vehicle that's going to go into space and go through acceleration and temperature extremes and atmospheric conditions that are unfamiliar and so on, very, very challenging project. So the goal was to, in a reasonable amount of time, come up with this design. So let me see if I can find this. I've been trying to look for it without looking like I was looking for it, and I did not. So here's a circuit diagram for part of the Apollo guidance computer. And it looks similar to diagrams that we're going to be drawing. And if you blow this up, what do you see every time that there's a picture of a chip? What kind of chip is this?
Nothing but NORs.
That's nothing but NORs. The whole computer was built out of NOR gates. Why? Because this way you only had to design one kind of chip. So the labs that built this came up with a NOR gate, tested it, stress tested it, documented it, and all the logic circuit was built out of NORs using this kind of approach. And this is just page after page after page of big ugly circuits with NOR gates.
What do the black ends mean?
I don't know. I think it's, if I had to guess, I would say it's a different kind of output that maybe has more current capacity or something like that. The other thing is, and I think that previous one has better examples of it, there are a lot of places where you see this kind of arrangement, where you see two of these gates and they're sort of cross-connected. The output here feeds the input here, and the output here feeds the input there. And it's kind of like two things connected together. We're going to see that a lot in about 2 or 3 weeks. That's how we're going to build memory elements. And we're going to create something that looks exactly like this using NOR gates or using NAND gates. So we'll come back to that in a few weeks. But this was the memory part of this particular circuit, and it could remember voltage levels, logic 1s or logic 0s. So that's how they built the memory.
Is that still how memory is stored?
That's how static memory is stored. It's a very fast way to store and retrieve memory, but it's really expensive because you need 2 of these gates to store 1 bit. So if you have 16 gigabytes of memory on your machine, that's 128 billion bits. That would be 256 billion gates, and each of those is several transistors, so it's about 1 trillion transistors. right? Static memory is really expensive. The main memory on your computer is what's called dynamic memory, and it basically uses little capacitors, little things that can hold a charge for a brief amount of time. And the capacitor is just two pieces of metal close to each other. Sometimes we touch on them in 120. Dynamic memory, the 16 gig stuff you can buy for a few bucks from Best Buy, is just a big array of 128 billion of these tiny little capacitors. Very cheap to manufacture, very reliable, but slow compared to static memory. So the cache inside your computer, if you know about cache memory when you're picking out CPUs, that's static RAM. That's spendy. That's why you only get, maybe a few megabytes of cache. So yeah, we still use this. All right, so moving forward, let's go back to sum of products. And let's go back to our combination lock. So remember, we had 3 inputs. And so here's our system diagram. So 3 inputs A, B, C. If you press the button, that's generating a logic 1. And we have an output which says unlock. And 1 equals unlocked. So 3 inputs and 1 output, unlock. And we had a secret combination which was 111 that would unlock our diary or whatever. And we had another secret combination we could give to our friend which was 101, and then everything else would leave it locked. And I don't know, we got a third friend all of a sudden, and so we give them a new secret code which is 001. So we have exactly 3 combinations that'll unlock this extremely secure mechanism, and the others leave it locked. So we can go through what we went through last week and write an equation for this, and let me just call this U. And this would turn out U is a sum of the following products. So remember, here we want the output to be 1, so the inputs are 0, 0, 1. If the input's 0, write down that variable with a bar on top. If the input's a 1, just write down the variable by itself. So U would be A bar, B bar, C, or here's another output that's 1. Okay, A has a 1, B is a 0, and C is a 1. Or one more term, A, B, and C are all 1, so this is just A, B, C. And we went through a long, detailed derivation of that on Thursday, but in the end, this is the equation you come up with, right? And this is what you're going to do for experiment 6 in lab 2 also, for that truth table. All right, so we have this equation. Doesn't matter what these variables are called. It doesn't matter what the purpose of this function is. Basically, anytime I have a truth table and I want to write an equation, I'm going to find where all the 1s are in the output. And then I'm going to write down some product term, some combination of the inputs, where if the input's a 0, I write that variable with a bar. If the input's a 1, I write the variable without a bar. We're going to do this again and again and again, and it gets really tedious, and there's a lot of extra information in here that we don't need. So we have some shorthands for writing equations like this. So we're going to define something called a min term. And the min term is just this product term corresponding to each input. So the min term for this first row is A bar, B bar, C bar. This is A bar, B bar, C, A bar, B, C bar, and so on. And if you write this a few thousand times, you get really good at it. And then if you have to do this on a test, it's like really second nature. But if you work through it, those are what the min terms look like. Well, instead of having to remember what these things are and write them down, we have abbreviations for them. We just call this min term 0, 1, 2, 3, up through M7. And as long as we know the order of these variables, if someone says M5, I know they mean A, B bar, C. Why? Because the number 5 is 1, 0, 1. So that 1 will give me an A, the 0 will give me a B bar, the 1 will give me a C. So we could actually say U, and I'm going to list the inputs so I know what order they're coming in. And I could say this is equal to, well, instead of A bar, B bar, C, I'm going to say M1 plus A, B bar, C is going to be M5 plus an A, B, C is going to be M7. So this is called minterm form. This is called sum of products. And sometimes we write it like this, which is called compact minterm form. And we're kind of abusing the summation symbol to say we're going to add these three things together, M1, M5, and M7, instead of writing the plus signs in between. But any time that we're talking about a sum of products, and that sigma means sum to us, anytime we're talking about a sum of products, these products are always minterms. So we don't even need to list the m. So sometimes we'll just write this as sum 1, 5, 7. And this is sometimes called implicit compact minterm form. And so this might be called explicit. So a lot of terminology. The main thing to know is if you're asked to write the sum of products, spell it out. If you're asked to use minterm form, you can use the m's as an abbreviation. And usually this, or this, I'll accept any of those. But think about this last expression here. How much work did I have to do to write down this equation? I just looked at this and I said row 0, 1, 2, 3, 4, 5, and 7 are the ones where I have 1s. Sum of 1, 5, 7, I'm done. That's my equation. So it takes some work still to understand that this means that, but to somebody who understands compact minterm form, this completely specifies the truth table. And so that's a huge time saver. And it's also less error prone, because once you start writing these things out, you're going to make mistakes. There's going to be typos, right? This is very clear, rows 1, 5, and 7, unless you miscount. All right, questions on that? And everything we're talking about today is sum of products. Thursday we'll talk about product of sums, and it'll flip everything around, but it's going to be sort of a dual to everything we're doing here. We're going to have max terms, and we're going to take a product of max terms, and we'll find a way for writing each of these max terms based on the inputs. And it'll be similar, but kind of flipped over in some ways. But we're just doing sum of products for now. Okay, well, there's something else we can do in truth tables. We can also introduce what's called a don't care. And we specify this on an input. Sorry, specify this on an output. Okay, what's an example of a don't care? Let's say, yeah.
I was going to say like any value that isn't 1 for unlock on the previous example.
Any value that isn't
Any output that isn't 1.
we still care about those. So for example, we really want this to be a 0 because we know if it's a 0, the door is going to stay locked. But it may be that there's an extra button. Where can I find an example here? It's not going to work with this example. Let's say we're building a circuit, and here's an A, and here's a B, and here's a help button, which we can use for some purpose. And let's say this generates, I don't know, this is not going to work as a good example. Let's just say it generates some output X. And we've got 3 inputs, A, B, and help. And we've got outputs X and Y. And if you don't press the help button, then X is, I don't know, maybe it's doing an OR gate. And Y is a 0. But if you generate the help button, then if you press the help button, we want Y to be a 1. And it may be, whatever this crazy circuit is doing, that if Y is a 1, we don't care what the value of X is. Okay, maybe this is going to reset the system or something like that, and the value of X is going to be totally ignored. And it may be that in these cases, we just don't care what the value of X is. Make it a 1, make it a 0, makes no difference, because this is somehow going to do something more relevant. So if we were to try to write an equation for X, we could do the regular sum of products thing. But what are we going to put down here? Are we going to put down 0s or 1s? Well, if we put down 1s here, right, then this output X is going to be the sum of min terms 1, 2, 3, 4, 5, 6, 7. It's going to be 7 products getting added together. So we're going to need lots of AND gates. We're going to need a big OR gate that can take 7 things. If we chose to make these 0s, then we only have these 3 1s. We'd only have a sum of 3 products. So there may be cases where making these all 0s, you're making them all 1s, you're making this a 0, 0, and this a 1, and this a 0, might simplify our logic. So if you have a truth table where there's these don't care values, you can fill them in however you like. And sometimes filling them in the right way simplifies your logic. And so we're going to come back to that with some more specifics. But in compact form, so this is min term 0, 1, 2, 3. If I were to write X in compact form, this would be sum of 0, 1, 2, 3. We have this other notation we can use. We can say plus MD 4, 5, 6, 7. This means don't care. And I mention that because you'll see that in the textbook. So if you add MD of something, it means we don't care what the outputs are for those. And we'll come back to why that's important when we get to K-maps. All right, so let's go to the board. Let's do some circuit simplification. So pick your groups and find a spot on the board. Probably 4 people to a group. And I'm going to ask you to write the following truth table. So fill this truth table out. So your second and third terms are 1s, everything else is a 0. and then using the idea of sum of products, come up with an explicit sum of products for X in terms of A, B, and C. Just by writing down the two product terms that correspond to those ones. And then we're going to play with that.
And then what?
Oh, so this one. I'll do it first.
Is that? Oh, yeah, like.
It's going to be M0 through 7, right?
Yeah.
So,
And then once you have a sum of products, very neatly below that, see if you can simplify that equation.
okay. So, it should be.
And think about factoring something out.
Or A bar B C.
So these are its.
That looks good.
And then we're doing M, the min term.
I think this would be M2.
So then summation 1, 3, or 2, 3. 2 comes. I think it's everything, right? Yeah. Sure. Or just get the last one going and just say M1 plus M2 plus M3 equals. And we're going to do the implicit and explicit as well. Just the OG. Cool.
All right, so that looks perfect. Can you simplify that equation by factoring something out?
Oh.
And that's a good compact form also, by the way. Can you simplify? Okay, so that's a good compact form. Simplify that? Yeah, why?
So these inputs, AB and AB are the same.
So pull out C or C.
A bar B.
Oh, yeah, because C doesn't matter.
All right.
Well, C is the only one that.
All right, so everybody has gotten this. So we can factor out, just like we do with regular algebra, we can factor out that A bar B,
There you go.
and we know that either C bar or C is going to be true. One of them has to be true. If C is true, this is true. If C is false, then C bar is true. So this is always a 1, and anything added with 1 is just that anything, so this is equal to A bar B. So that's a simpler way to write this equation for X. It's just A bar B. And there's a theorem, it's called the Adjacency Theorem, which basically says XY or XY bar is the same thing as just X. In this case, our X is A bar B and our Y is C. So XY or XY bar is just X. Why is it called the Adjacency Theorem? Because this happens when we have two adjacent rows in our truth table that are both equal to 1. And if you look at this, the inputs are exactly the same on this row and this row, except for this last variable, C. If it's a 0, the output's a 1. If it's a 1, the output's a 1. C doesn't matter. So anytime that you write your truth table and you break it into groups of 2 and you see 2 adjacent rows that are both equal to 1, we can ignore this last variable. And we can just write the min term for these 2 variables, A bar ended with B. That's a simplification. Okay, that works great if we happen to have this property in our truth table. Let me show you a different truth table with a different function. And unfortunately, we don't have any adjacent rows that are both equal to 1. But here's what I want you to do. This is the truth table describing our function. I would like you to rewrite the truth table, but label your inputs B, C, and A, and your output X. And keep the same ordering. But fill in this truth table based on our original truth table and see what happens. But hold on, because I messed up. Don't do that yet. Okay, yeah, go ahead. I did not mess up.
So we're just, that is still saying,
Yeah,
just normal, okay.
it's going to be the last 2 that are going to be. Yeah, it'll be the last 2 that are going to be. And now 1.
These are all, if you look at the original one, this one, these are
So these ones should be 1 because B and C are the only ones that really matter. This was 1 that should just be 0. And then it's going to do this, and then it's going to be 8, right? Or BC is the only thing that matters. So would it just be BC? Yeah.
yeah, I meant like
Yeah.
So what is this? This is A, R, A, yeah.
Because C plus or C is always true.
It's always true.
And
Yeah.
this is
So
not
C
A,
is,
B, C.
today is Sunday, right?
Yeah.
Either it's true or it's false.
Yeah.
So the or is always going to be true. So we have A bar ANDed with B, ANDed with something that's always true.
Okay.
That's just the same as A bar ANDed with B.
Right.
So you can just do this with B and 7 and 6 and 7.
And that would be this Oh, actually.
So which combination of input would give you a 1? So A is 0, B is 1, C is 1. So
yeah.
your BCA truth table, right? It's easier to see this if you number it in the usual way. 0, 0, 0, 0, 0, 1. To make a new table to represent the same information. the only thing we're doing here is we're drawing a different truth table. It's the same function though, right? We're putting the same value of x for the same combination of a, b, and c. We just happen to do it in a different order, BCA instead of ABC. And so this truth table is equally valid because there's nothing that says we have to put the inputs in alphabetical order, right? We always want to write our truth tables with the input bit pattern counting in binary 0, 0, 0, 0, 0, 1, 0, 1, 0. We're going to stick to that, okay, because that's pretty much a solid convention, but we don't have to alphabetize the inputs. I think we could do BCA because that's our dog's initials. Perfectly valid. So there's still only two input combinations that give x equal to 1, right? A equals 0, b and c equal 1, and a equals 1, b and c equal 1. Right, and so everybody's got this now. So that turns out to be these two rows on the bottom. And now if we look at this truth table, we can do our little adjacency trick. We can say, you know, these two rows right here, doesn't matter what the value of A is. A could be a 0, A could be a 1. As long as B and C are both 1, the output's going to be a 1. And we can immediately write x equals and just write down the product term corresponding to B equals 1 and C equals 1, x equals BC. So whereas this would have said x equals A bar BC or A BC, and we could have done some algebra to factor out the BC, say A bar or A equals 1, and then throw it away. If we happen to write our truth table like this, we don't have to do any algebra. We can just visually look at this and say, hey, here's two adjacent rows. I can throw away the A, x equals BC. And if there happened to be, you know, a pair of 1s up here, we could do the same thing there. Or maybe there happened to be a pair of 1s right here. And at this point, we could have said, hey, if C doesn't matter, this corresponds to x equals A ANDed with B bar. And so we could pick up these terms with this, and we could pick up these terms with this, and we could pick up these terms with A bar, with B bar C, right? So by rearranging the truth table's variables, we could save ourselves a lot of work theoretically. But this is a pain. There's a lot of different ways we could rearrange these variables. And unless we happen to stumble across the magic way that makes these things adjacent, right, this is probably more work than it's going to save us. But this is the idea of a K-map. It's a visual trick that will let us look at this truth table and write down things like this immediately. All right, so we got 9 minutes. Go ahead and have a seat, and let me show you how we use a K-map, just to do a first pass, and then we're going to break this down in detail on Thursday, and we'll spend a lot of time practicing on the boards. And I'm going to jump up to an input, a circuit that has 4 inputs, just to make it more complex, because it's more fun if it's more complex. You can quote me on that. When I draw truth tables, especially with 3 or 4 variables, I tend to block these off in groups just to keep them lined up. All right, so what kind of truth table do we want here? All right, there's a truth table with lots of 1s. 1, 2, 3, 4, 5, 6, 7, 8 1s. We're going to have 8 product terms. Each product term is going to be a combination of 4 inputs. So we're going to have 8 4-input AND gates with some inverters, and then we're going to need an 8-input OR gate. This is a big circuit. but we can guess there's probably some adjacency. We can see some adjacency down here already. So let's make a K-map. All right, so we'll keep this on the side as our truth table. Okay, here's how we make a K-map. And like I say, we'll do this again on Thursday. But let me just show you what this is going to look like. We're going to make a representation of our truth table as a two-dimensional picture instead of one. And I'm going to take my inputs and label them like this, A, B, and then C, D. And I'm going to put down all the possible values for A, B down this first column. And we're going to do this in a peculiar order. I'm going to do 0, 0, 0, 1, and then 1, 1, and then 1, 0. So this is one time we're not going to go in the regular standard binary order.
Is this like a Punnett square?
I don't know. I'll have to learn what that is. What is it?
Something you use in biology.
For genes.
Oh, okay, okay. Probably not. That would be cool if there was a connection, though. All right, so each of these squares corresponds to one row of the truth table. Here's a way to think of this. These are values of C and D, and these are values of A and B. So, for example, this fifth row, 0, 1, 0, 0. A is a 0, B is a 1. That corresponds to this row. And C is a 0 and D is a 0. That corresponds to this column. So this fifth row corresponds to this box. And what I'm going to do is I'm going to write down every place where there's a 1. So here there's a 1. 0, 0, 0, 1 corresponds to this second box here. So that's got a 1 in it. 0, 0, 1, 1, 0, 0, 1, 1, that's this box right here. 1, 0, 0, 0 is this box right here, so that's that ninth row. And then these last four rows, A and B are 1, 1, C and D are all the possible values, so that's this set of boxes right here. So I filled in all the ones. Okay, here's the fun part. We're going to do what's called covering the ones. So we're going to try to draw rectangles around the ones. And any rectangle we draw has to have a length of a side which is either 1, 2, or 4. We can't have rectangles with lengths of 3. But they can have a length and a height of 1, 2, or 4. And we want to find the biggest rectangles possible that we can draw so that we have the fewest number of big rectangles covering all the ones, but not covering any of the unfilled in squares.
Why isn't there a 1 in the upper right box?
Did I miss one? 0, 0, 1, 0. That should be a 0. So it should be 1, 2, 3, 4. Should be 8 ones. So I think that's right. Okay, so let's start making some rectangles. Well, I can cover these ones with a 1 by 2 rectangle. And there's a bunch of ones I can cover here with a 1 by 4 rectangle. Now you got to cover every single one. You can cover things more than once, but you have to cover every one, and you're not allowed to cover any zeros. So to cover this one, I could draw a rectangle like this, but I could make a bigger rectangle like this. I could try to make a rectangle to cover all 3, but my rectangles can't have a height of 3. It's got to be 1, 2, or 4. And if I did all 4, I'd be covering a 0. So the best I can do is to cover the 2 of those. And I can make another rectangle to cover these. So that's a good covering of the ones. And we'll pin down the precise rules for doing this. Okay, what we've done is we've identified where we can use the adjacency theorem. And by drawing our truth table like this, visually things that satisfy the adjacency theorem are next to each other, either horizontally or vertically. It's a cool little visual trick. And now all we have to do is write down this product term corresponding to each of these rectangles. And there's a way to do that. And we'll detail it on Thursday, but I'll just give it to you here just so you can see how efficient this is. This is going to correspond to the product term A bar, B bar, D. This big box is going to correspond to the product term A, B, just A, B. This purple rectangle is going to be the product term C bar, D bar, A. And the green rectangle is going to be C bar, D bar, B. And our final expression will be this, ORed with this, ORed with this, ORed with that. And it's a very succinct representation compared to our original truth table, which was 8 product terms, each with 4 inputs. So we'll break this down as an algorithm. We'll see exactly how to come up with this covering, how to write down these terms, and then we'll also see how to deal with don't cares. And don't cares make this even better. But this is a fun way to simplify equations. So we'll go through that in detail on Thursday, and then we'll spend a lot of the class just on the board, filling these things in, covering the rectangles, writing equations. We'll get lots of practice with that. And then that'll be a big part of what homework 3 is just doing some K-maps. All right, so I will see you on Thursday.